let me start by thanking the organizers, Martin, Timo, and Otmar, for putting together this series. It's been so great to be a part of it. And I should also thank Jacob and others behind the scenes who've also been ensuring, in addition to the organizers, that everything's been running so smoothly. So today, I would like to talk about some work on explicitly computing rational points on curves. So not just some of the results, but really the tools behind the scenes, mostly the computers behind the scenes and the computer packages that have allowed us to say anything about rational points on curves. So just to start off with, the question is, well, which curves can we say something about? Now the discussion will primarily focus on curves of genus 2 or more, but maybe on the lower end. So genus 2 through, I think, 6 is where we have a number of examples. And then also possibly the class of modular curves. As far as infrastructure, I think this is an important part of the discussion. So behind the scenes, a lot of what we do requires other components, other tools that many other people have spent years working on, so that things things run smoothly and things can get carried out, hypotheses verified. So for instance, being able to compute the Mordell-Weil rank of the Jacobian, or being able to take your curve, or even to construct a curve in magma, and then to say, okay, I want this curve to be over a p-adic field or maybe an extension. Where do you even go to look for sources of curves? Of course, we know that we like to look at modular curves, but then perhaps we're interested in other curves that might have other properties. And I thought I'd just say a few words about the L functions and modular forms database, which has a lot of rich data, in particular the case of genus 2 curves. Now, the tools that I'd like to talk about, once we have some of that infrastructure in place, is to compute single Coleman integrals, double Coleman integrals, feed that into the Chabauty-Coleman method, as well as some other techniques like 2-cover descent, elliptic Chabauty, and then some other tools for quadratic Chabauty, like p-adic sigma functions and p-adic heights. Right, so the first bit of infrastructure, so a lot of what we do, we start off by saying, well, suppose the rank of the Jacobian is this, where maybe it's less than the genus, or it's equal to the genus, or whatever it is. But in general, it is rather difficult to compute the Mordell-Weil rank of the Jacobian of a curve. So I thought I'd just point out that magma has an implementation of descent on Jacobians of curves that are cyclic covers of P1, thanks to the work of Brendan Kreutz and others. If it turns out that the curve that you're looking at is modular, well, then maybe you can compute analytic ranks and then possibly deduce rank using Kolobov and Movichev. Now, as far as getting data, especially if you have a conjecture that you'd like to test, or you'd like to just browse and maybe discover new patterns among structures that you've been looking at, well, the L functions and modular forms database is a great resource for this. In the case of genus 2 curves, there is a very nice database thanks to the work of Andy Booker, Jeroen Seisling, Andrew Sutherland, John Voigt, and Dan Yasaki. And there are 66,158 genus 2 curves over the rationals with various properties. And you can either filter through this list for various things that you're looking for, maybe analytic rank 1, for instance, or a certain automorphism group, and then you will get a list of curves for which you can try out your conjecture. I think this is a really valuable resource, and I know I've used it a lot, my collaborators and the students as well. So I just wanted to give a shout out to LMFGB, and I know more curves I think are on the way, and possibly even higher genus curves as well. All right, so we saw in the last lecture a little bit about the Chabauty-Coleman method and some of the successes it's had in determining rational points on curves. I just thought I'd briefly recall the setup of Chabauty-Coleman. So Coleman observed in 1985 that one could make Chabauty's theorem effective by translating it in terms of p-adic integrals of regular one forms. So these p-adic integrals are what we call Coleman integrals these days. These are certain p-adic line integrals that Coleman constructed. And it applies in the case when the Jacobian rank of the curve, R, is less than G, the genus of the curve. And when it applies, one can construct an annihilating differential omega, a regular one form omega, that annihilates rational points, but maybe at the expense of also annihilating some extra p-adic points as well. But in any case, there is a finite set xqp1 that is cut out by the zero locus of the integral or integrals of annihilating differentials. So to carry out this method, we would like to compute a basis for the space of annihilating regular one forms, and then to calculate this finite set of p-adic points, xqp1. We've seen that this has worked out very well in practice. In general, it uses the explicit computation of Coleman integrals to be able to do this linear algebra to construct an annihilating differential. So I should tell you a little bit about p-adic integrals, about Coleman integrals and how we compute them. I mentioned that Coleman integrals are really p-adic line integrals. And maybe that had you worried because you had some picture like this in your mind. What does it mean to construct a path between 2 points in some p-adic space? So locally, maybe there's less of a worry. So what I mean by that is, well, if you have 2 points, say P and P prime, that are close by p-adically, so say they reduce to the same point mod P, the special fiber, well, then you can construct a line integral or path integral between those 2 points by the usual method where you construct a uniformizing parameter at one point and then compute a power series expansion in a disk to then write your differential form and then integrate that. So locally, there's a sense of integration that maybe is not so worrisome. But then what do you do across the whole space? So if you were to do this across every neighborhood, across every residue disk, how do you know that you've done something compatible? Well, Coleman's solution to this was to bring Frobenius in and to say, well, Frobenius fixes a path between 2 points. Regardless of the residue disk, we have some notion of analytic continuation along Frobenius. And this will give us a nice theory of p-adic line integration that satisfies some of the properties that you'd expect an integral to satisfy, such as linearity or additivity or change of variables or the fundamental theorem of calculus. So the Coleman integral has all of these nice properties. And the main idea is to compute the action of Frobenius on the differential that you're interested in integrating, or maybe a collection of basis differentials, and then reduce back to this basis using some relations in cohomology, and then integrate by doing some linear algebra. And I will say more about how this gets carried out in practice. But maybe I should just say a few words about some of the properties the Coleman integral satisfies to convince you that this is a reasonable thing to try to compute, and that there are indeed several nice properties that we can see here. So if I take a smooth projective curve, just to simplify the discussion over QP, and I'll assume it has good reduction at P, Coleman showed that this p-adic integral between 2 points P and Q of a regular one form omega satisfies these properties. So first, the integral is linear, is QP bar linear in the integrand omega. If I want to compute an integral between 2 points that reduce the same thing, the special fiber, P bar, then that's what we call tiny integral. And we can compute it by writing down a uniformizer at one of the endpoints, say P, it doesn't matter which one, but suppose we pick P, and then writing down the differential omega in terms of that uniformizer T, and then integrating that power series formally, which gives us a power series L for which the derivative is omega T dt, and which we have constant, we have zero constant coefficient. And then finally evaluate L at the other endpoint. So L at the parameter corresponding to the other endpoint. This converges in this residue disk, and moreover, it implies that the integral between a point and itself is 0. Now we can also kind of mix up our endpoints in the following way. So we integrate from p to q and then p prime to q prime. This is the same as the integral from p to q prime plus p prime to q. And so it's a sensible thing to define an integral along a degree 0 divisor as a sum of the corresponding integrals. And we can then compute integrals along principal divisors and show that they are 0. The integral is also compatible with natural Galois action. And finally, if we were to consider an integral from a fixed point p naught, and then say in the same way, compute an integral from that point p naught of some omega, then within a residue disk, the number of zeros that power series expansion of the integral can have is finite. So the set of points p reducing to the same point in the special fiber such that the integral vanishes between p naught to p. That's that set of points is finite. And that just comes from a p-adic Weierstrass preparation statement. All right, so where do we start with computing p-adic integrals or Coleman integrals once we know some of these properties? So one way to do this is to start with a zeta function algorithm that computes the action of Frobenius. Since we said that that's really what we want to use, the fact that Frobenius is going to fix a path between 2 points. And so if we have some way to compute the action of Frobenius on differentials, then we're in business. So one way of computing the zeta function of a hyperelliptic curve over a finite field comes to us from Kedlaya's algorithm. So he used Monsky-Washnitzka cohomology to do this. And we can turn Kedlaya's algorithm into an algorithm for computing Coleman integrals on hyperelliptic curves over the p-adics. This was work that Bradshaw-Kedlaya and I did about a decade ago. Now, more long-term, we'd like to adapt various generalizations of Kedlaya's algorithm in various directions to give Coleman integration algorithms in new contexts. And so what do I mean by that? So here is a big picture kind of tying together all the different directions in which we might, or some of the directions in which we might hope to extend Kedlaya's work. So in the beginning, there was Kedlaya, and Kedlaya told us how to compute zeta functions of hyperelliptic curves over finite fields using Monsky-Washnitzka cohomology. This was then extended by a number of people interested in looking at other curves or families of curves. So Kastrick, Denef, and Vercaterin did this for non-degenerate curves, Gaudry and Gorel for superelliptic curves, Hubrechts and Lauder for families of curves. And then most recently, Jan Tuitman gave a practical algorithm for doing this on smooth curves and gave a lot of really nice examples showing that this really is something that you can implement on a computer and get some very nice results. Now, in a different direction, one can build on Kedlaya's algorithm and talk about p-adic integrals and p-adic heights. So this is where some of these Coleman integration algorithms come in. This is the work that I mentioned that Bradshaw and Kedlaya and I did, and I'll say more about that in a moment. But I should also say that Mazur, Stein, and Tate gave a very nice algorithm building on Kedlaya to compute p-adic heights on elliptic curves. And then Besser and I did some related work to apply this to the Coleman gross height for Jacobians of hyperelliptic curves. All right, so you can imagine combining these two directions and taking, for instance, Coleman integrals on more curves, or looking at Coleman integrals in families of curves, or p-adic heights on more curves, or p-adic heights in other families of curves. So what Jan Tuitman and I did was to study Coleman integrals for more general curves, building on his zeta function algorithm. So we have some tools for computing Coleman integrals on smooth curves and a magma package for this, and I'll say more about this in a moment. I also wanted to mention some nice work of my student, Francesca Bianchi, who computed p-adic heights in families of curves and also p-adic sigma functions in various directions, extending some of the earlier implementations. Now, there's yet one more dimension that we can add to this, that at least fits into this diagram, which is to do everything faster. So David Harvey gave a really nice enhancement to the work of Kedlaya, translating some of the reductions in cohomology into linear occurrences. He improved the complexity of the algorithm. And so it's much faster to do Harvey style improvement to Kedlaya for large prime P. There's implementations of this available. So you can then try to combine this with some of what we have so far. And so Minsloff and Arul, Best, Costa, Magner, and Triantapoulou did this for superelliptic curves for cyclic covers of P1. So they have fast zeta function algorithms to do this. And then we still have a few more things that we can kind of complete in this diagram. And my student, Alex Best, started by taking Harvey's work, the fast zeta functions algorithm, and added Coleman integration to that and show that one can compute Coleman integrals fast in a Harvey style way. But there's also more to be done. And so in the last vertex here, to compute Coleman integrals faster for more curves. So that's something that Best recently did. He computed Coleman integrals for superelliptic curves over unramified extensions of QP even faster. Alex just recently graduated, so I thought I'd just say a little bit about some of the work that he did. Right, so the bits that I highlighted in yellow are some of the tools that I'd like to talk about for computing rational points, especially in the Coleman integration directions. Now, there's also more that we could say, though I only have these 3 spatial dimensions and I didn't really have the space to add these things, but just for those that are interested, one can do even faster zeta functions and hopefully extend this to Coleman integrals and so on via the average polynomial time algorithms of Harvey. There's extensions to iterated Coleman integrals. So Coleman gave iterated versions of all of his theorems, and I gave an algorithm to do this for hyperelliptic curves. And one can also compute zeta functions of higher dimensional varieties, thanks to the work of Costa, Harvey, and Kedlaya. So hopefully all of these things can be combined in this ecosystem and give us more algorithms and more tools for computing with rational points. And I should also thank Alex Best for helping me with this diagram and producing a very nice version of this to kind of collect all of these ideas in one place. All right, so from zeta functions to Coleman integrals, the idea is we want to upgrade Kedlaya's algorithm to an algorithm for Coleman integrals on hyperelliptic curves, and then show how this extends in 2 ways. First, to general curves in the way that Jan Tautman and I did, and then the way that Alex Best did to show how Harvey's adaptation of Kedlaya's algorithm can be used to give faster Coleman integration for large primes P. So just to fix some notation and set up for what comes next, X will be a genus G hyperelliptic curve of the form y squared equals f of x, where f is monic of odd degree over QP for simplicity. P will be a prime of good reduction. X bar its special fiber, and XCPAN is generic fiber is a rigid analytic space. And then a few pictures to keep in your mind as we talk about some of these algorithms. So we have a natural reduction map from the generic fiber to the special fiber, and the inverse image of any point in the special fiber is a subspace upstairs that's isomorphic to an open unit disk, and that's what we mean by a residue disk. Then there will be some bad points that we won't want to integrate near, and so we'll delete some finite collection of closed disks of radius less than 1 And what's left over in the space is called a wide open subspace. All right, so just to warm up, these are our first Coleman integrals that we'll compute. So these tiny integrals that I mentioned earlier that happen in the same residue disk. So we're going to assume that our points P and Q reduce to the same point, mod P. And we have some regular one form. So to compute one of these integrals, we're going to expand omega in a local coordinate T on the residue disk, either at P or at Q, it doesn't matter. And then formally integrate the power series term by term, and then evaluate the corresponding parameters associated to the endpoints. So that's perhaps what you expect. If you have an integral, it's a natural thing to try to do. And this is sensible within a residue disk. All right, but then we need to move between residue disks. And as I mentioned, Coleman's idea was to use Frobenius to move between different residue disks. This principle of Dwork to analytically continue along Frobenius. So we need to compute the action of Frobenius on differentials. And so I just wanted to set up some of the objects behind the scenes. So we're going to consider this particular affine curve where we delete the Weierstrass points of X and consider A its coordinate ring. And then compute the Monsky-Waschnitzer weak completion of A, this ring A dagger, that looks like infinite sums of the form in the numerator polynomials in X bounded by 2G, where G is the genus of the curve. And then the denominator various powers of Y. So this is now then subject to the condition that the valuation of the polynomials bi grows faster than a linear function of I as I goes off to infinity in either direction, some notion of overconvergence. And we will make a ring out of these using the relation coming to us from the equation of the hyperelliptic curve. Now these functions are holomorphic on wide opens, and so what we will do is integrate one forms that look like some element here in the dagger ring times dx over 2y. Now, any odd differential, so odd with respect to the hyperelliptic convolution, can be written as some df omega plus a linear combination of these differentials omega I that are of the form x to the I dx over 2i. Remember, we're looking at hyperelliptic curves, so this is maybe a natural, nice basis to consider. But what this is saying is that if I consider the de Rham cohomology of A dagger, and in particular the odd part of it, so the minus eigenspace under the hyperelliptic convolution, I have this 2G dimensional basis given by the usual differentials that you would expect to see. And then by the properties of the Coleman integral, so in particular using linearity and the fundamental theorem of calculus, we can reduce the integration of omega, the differential that we want, to the integration of one of the basis differentials, omega I. So now we've broken the problem down into computing the integral of one of the basis elements, omega I. All right, so now Frobenius comes in, and we'll let phi denote a lift of p power Frobenius. So on our hyperelliptic curve, this is something that we can write down reasonably nicely. This is part of what Kedlaya did. So he picked the particular lift of Frobenius that looks like x sending x to the p, and then y going to where it has to go. But he showed that one could write this in a reasonable way using a binomial expansion and showing that it had nice convergence properties. Now we'll also reduce in some cases to points that are fixed by Frobenius, so-called Teichmüller points. So essentially you take the Teichmüller lift of your x coordinate and then solve for the corresponding y coordinate. And you can do this in every non-Weierstrass residue disk. All right, so one way to compute Coleman integrals between any two points, P and Q, is to first find these points that are fixed by Frobenius in the corresponding residue disks. So to compute the corresponding Frobenius fixed point P prime, and also the corresponding Frobenius fixed point Q, call that Q prime, and then use Frobenius to compute the integral between P prime and Q prime. We'll say much more about that in just a moment. So there's this Frobenius step that's quite important. But then you can use additivity and endpoints to correct and get the integral that you actually wanted between the 2 points P and Q that you started off with. All right, so this is the Frobenius step. This is Kedlaya's algorithm. So we had this p-paraelliptic Frobenius, and I earlier said, well, we send x to x to the p, and we send y to where it has to go. And so if you work things out, y kind of looks like this, where it looks, you're taking this binomial expansion of the square root, and looks like, well, you now have many, many terms that you have to consider. But part of what Kedlaya did was to show how many terms you would need to consider in this expansion of y. And in particular, that's some finite truncation that you can take if you want to know your eventual results up to some p-adic precision. One can go through and work out all the different terms needed, and the amount of p-adic precision needed at each step to ensure provably correct results. And then with this, we can apply our lift of Frobenius and pull it back to a differential omega I. So remember, omega I was dx over, so x to the I dx over 2y. And so we're going to send x to the p. And so in the numerator now we have an x to the pi and a d of x of p, x to the p, and then 2 times the Frobenius on y. Let's just kind of expand some things that we can. We take that derivative and combine some terms. And then we have to worry a little bit about what Frobenius on y looks like. All right, so it looks something like that. And maybe you combine some terms and do a little bit more of simplification here. But essentially, Kedlaya's algorithm says that, well, first, there's some finite truncation of this infinite sum that you can take. And moreover, it looks like you've introduced this horrible pole order, this y to the minus p, just that you have on the outside, but then y to the 2p n for some very large n, right? And how do you tame that very large pole order and reduce within cohomology? So there's some p-adic magic that happens. Essentially, there's some systematic linear algebra that you do along the way to reduce the pole order and subtract off various linear combinations of d's of different monomials at each step. And then you can collect all of those sums of derivatives or differentials into this term dfi. So the sort of garbage collection along each step, what in cohomology is just 0, it turns out to be very important for us here. We need to know what this dfi is at the very end of the reduction. And then what you're left with, that's what you would like to compute. If you're looking at the zeta function, you'd like to compute the characteristic polynomial of this matrix M. But for Coleman integration, you really do need both. You need this dfi plus the matrix M. All right, so the output of Kedlaya's algorithm is this expression that the pullback of Frobenius on some omega I can be written as a linear combination of the basis elements plus this exact form, this dfi. All right, and then now we plug this into our setup. So we have Kedlaya's algorithm, which calculated the action of Frobenius on each basis differential. And then we compute the Coleman integral between our Frobenius fixed points by solving the linear system. So we set it up. We say, okay, well, we know by construction, these points p prime and q prime were fixed by Frobenius. So let's just write that down. And then we can pull back Frobenius into the integrand. And then use this expression that Kedlaya's algorithm gives us and make the substitution so that the pullback of Frobenius has this expression dfi plus linear combination of basis elements. And then we have some nice properties that let us work with this and simplify as we go along. So we can break apart these two terms and then use the fundamental theorem of calculus to pull out some constants. And then finally, we imagine doing this not just for one basis differential at a time, but for the entire basis at the same time. So we can solve a linear system using the fact that we know what the eigenvalues of the matrix of Frobenius look like. They're algebraic integers of norm root p. In particular, they are not 1. And so the matrix M minus identity is invertible, and we can solve the system to get the integrals between the Frobenius fixed points. Right, so computing the integrals between these Teichmuller points amounts to some linear algebra once we know the action of Frobenius on basis differentials. Then there is a little bit more that we have to do. Remember, we did all of this in our setup. We deleted the Weierstrass points. Our lift of Frobenius doesn't behave nicely at Weierstrass points, but all of this overconvergence kind of helps us out in that we can extend slightly and work a little bit into the boundary of a Weierstrass residue disk. So what we do is, if we want to integrate from a Weierstrass endpoint P to some other point, we find a point near the boundary of the Weierstrass residue disk, so some point R, and then the integral from P to R, that's happening within the Weierstrass residue disk, so that's just a tiny integral that you compute, and then by overconvergence, you're able to compute the remaining integral, the integral from R to Q. And this requires now working over some extension of the p-adics, but this is doable, at least in the cases that we've tried for hyperelliptic curves, and reasonably practical, it seems. All right, so just some notes. This has been implemented for hyperelliptic curves over QP and available in Sage Math. But I should mention that this would not have been at all possible without the work of David Rowe and others in developing the p-adics in Sage Math. David spent countless hours writing the p-adics and rewriting the p-adics. So there was a lot of work that went on behind the scenes to even make it possible for us to compute Coleman integrals just over QP. And of course, one could hope to do this over extensions of QP as well. So here's just a little bit of code to show you what it might look like if you were to try to compute some Coleman integrals on hyperelliptic curves in Sage Math. You first set up a polynomial ring, then write down a hyperelliptic curve with some defining polynomial, instantiate some prime p and use that to create a p-adic field up to some precision. Here we've chosen 15. We take our hyperelliptic curve and say, okay, now I want to consider it over this field K, this 3-adic field with 15 digits of precision. And then I can compute Coleman integrals between 2 points. Behind the scenes is picking the spaces that I mentioned earlier. And then we get this vector of 4 numbers, 4 3-adic numbers, where, again, this just corresponds to the 4 elements of H1 Duran. All right. So then extending this to smooth curves, this requires some of the work of Tuitman, extending these p-adic point counting algorithms. And so in one quick slide, I thought I'd just give you a dictionary between the work of Kedlaya and going to Tuitman's work. So Tuitman wrote 2 papers where he extended these ideas, computing the action of Frobenius now on rigid cohomology for smooth projective curves. The basis of cohomology that's used, or the basis of H1, is a bit more complicated. So we saw for hyperelliptic curves, we just chose x to the I dx over 2y. Here, we don't necessarily need to see, and maybe some of these don't worry about it sort of moments. The computer essentially works in the function field of the curve. There is a low degree map, typically from the curve to P1, that's used to represent functions and one forms on the curve, and then some algebra in the function field of the curve. Then Magma gives you a basis that you typically don't need to see unless you're actually explicitly trying to figure out what basis elements are being used. The lift of Frobenius that you have is just the usual one where x goes to x to the p, and then depending on, well, what your model that you've passed in, you can kind of figure out what y has to be. So this is typically a Newton iteration to figure out what the corresponding lift on y looks like. The reduction cohomology is in spirit very similar. It's some linear algebra reducing the pole order that shows up once you've applied the action of Frobenius. And the output is exactly the same, where you have some exact, some df, and then a linear combination of your basis elements for each basis differential omega I. So using Tuitman's work on point counting, Jan and I wrote a magma package that is available on GitHub. And here is how you would call it on a superelliptic curve. So this is the superelliptic curve y cubed equals this quintic polynomial, and over the 7 adics with 20 digits of precision. We've picked 2 points on the curve and then computed the Coleman integrals on the basis that's kind of picked behind the scenes that Magma picks for you. And then we get some 7 adic numbers. All right, so now moving in the fast direction of applying Harvey's enhancements to Kedlaya and the work of Alex Vest to combine this with Coleman integration algorithms. So what Harvey's algorithm, so maybe to start with Kedlaya, Kedlaya's algorithm gives that the action of Frobenius on H1, on this odd part of H1, can be computed in time soft O of P, where that's just ignoring the log factors that show up. Now, Harvey showed that if P is sufficiently large, then this action can be computed in time soft O of root P. For both zeta function algorithms, what is needed is finding this matrix M of Frobenius, and they don't need the error terms, these terms dfi along the way that you're subtracting off. But for Coleman integration, we really do need those FIs. They give us the constant of integration, essentially. So in Kedlaya's algorithm, the reduction process at each step really does construct for you the FI. If we could subtract some dg for a monomial g to reduce the pole order of the action of Frobenius on a basis differential, then the new FI is the old FI plus whatever this g was. So Harvey restructures the reductions in terms of linear occurrences and keeps track of the reductions that lower the degree in x, what he calls the horizontal reductions, and the vertical reductions, the ones that lower the degree in y, in the denominator. He uses the work of Bostan, Gaudry, and Schost to give a fast way to compute a product of these reductions, which then give you Kedlaya's algorithm in a slightly different way, so in terms of these linear occurrence relations now. And then to extend this to Coleman integration, we also need to figure out how to take care of the subtractions at each step for these exact forms. Right? We need to also keep track of the evaluation of these functions g on points, since that ultimately is what gives us the constant integration. But this is no longer going to be linear in the reduction index. And so this algorithm of Bostan, Gaudry, and Schost no longer applies. So Alex had a very nice idea, which was to use Horner's method to compute the evaluation of g. So instead of doing this sequentially, to compute this as this nested product from the inside out, which is an iterated composition of linear functions, each of which is linear in the reduction index. And Alex Vest was able to use this to give a soft O of root P Coleman integration algorithm for hyperelliptic and then most recently superelliptic curves. So he made this available as a package for superelliptic curves over unramified extensions of the p-adics in Julia, building off of the NEMO computer algebra system. So Alex made this available on GitHub. I should maybe just say a few words about NEMO, since that might be a system that's new to some of you. So this is a relatively new system for computing in commutative algebra, number theory, and group theory that's based on some libraries like MPIR, Flint, ARB, and Antic. So this is based on the Julia language, and it's maintained by Bill Hart, Tommy Hoffman, Klaus Fieker, and Fredrik Johansson. Now, I briefly mentioned that Coleman gave a construction of iterated integrals as well. And in the non-abelian Chabauty method, one would like to compute some n-fold iterated Coleman integrals as well. So just to say a little bit about the case of n equals 2, since I think this will give you the main idea about how to do this more generally. So if I want to compute a double Coleman integral between points p and q, what I mean by that is I'm going to integrate from p to some dummy variable r, and then that gives me some series in terms of r. I rewrite my differential, my second differential, omega I in terms of r, and then integrate out. So that will give me the integral from p to q of omega I, omega j. So really there are two integrations happening. I just suppress one of the integrations in the notation. So as before, we would like to reduce to the case of these Frobenius fixed points between non-Weierstrass disks in the case of hyperelliptic curves. It's just that there's a little bit more bookkeeping to recover the double integral. So we no longer have this nice additivity in endpoints. That was the 3 terms. Now we have a few more error terms given in terms of products of single integrals. So we still like to compute the Tuitman points and use Frobenius to compute the integral between Tuitman points, but then to recover the double integral between the 2 points we wanted just requires a few more terms. The Frobenius step happens in a very similar way, where you just set up the fact that you have points that are fixed under Frobenius and then pull back into the integrand, and then apply the action of Frobenius using Kedlaya's algorithm, and then work out what this means, and essentially relate all these double integrals to single integrals and other terms that you can previously compute. So essentially, this is all kind of inductively happening. Once you're able to compute an n-1 fold Coleman integral, you can compute an n-fold Coleman integral. So here are all the constants that appear once you do that bit of algebra, rewriting and reducing to single integrals and other constants that pop out. And then you do some linear algebra to produce the Coleman integrals on all the different pairs of basis differentials that you care about. And again, we can invert the identity minus m tensor with itself, just again knowing the eigenvalues of this tensor squared matrix is. All right, so then as far as implementations go, so Chabauty-Coleman actually in magma is natively implemented in the case of a genus 2 curve over the rationals of Jacobian rank 1 or 0. And this is thanks to the work of Niels Brown, Michael Stoll, and the magma group, some of the infrastructure behind the scenes. Here is what it looks like if you were to call the Chabauty solver in magma. So it also, if necessary, carries out the Mordell-Evasive, and so essentially carries out Chabauty-Coleman at a collection of good primes and then sieves out using some information from the Jacobian. But I just wanted to mention that we could also try to use any of these Coleman integration packages that I mentioned to write a Chabauty-Coleman solver in SageMath, Julia, or Magma. Magma in the case of higher genus curves, since the current implementation is just for genus 2 curves of the relative of the rank 1 or 0. So we also have a few more packages for computing rational points. The first that I wanted to mention is the idea of using a 2-cover descent. This is work of Niels Brown, Victor Flynn, Daniel Hast, Michael Stoll, and Joe Weatherall on explicitly constructing a covering collection by pulling back under the multiplication by 2 map on the Jacobian of a genus 2 curve and finding suitable quotients. And then typically one combines this with elliptic Chabauty, using the fact that you realize a certain genus 5 quotient or its Jacobian as the restriction of scalars of an elliptic curve from a quintic field down to Q. Daniel Hast has implemented this 2-cover descent in Magma and has made this available on GitHub. And they use this to compute rational points on some genus 2 curves with Jacobian ranks 2 and 3, some cases under the assumption of GRH. And an implementation of elliptic Chabauty, this restriction of scalars idea, if you map down to an elliptic curve over a number field, that is available natively in Magma. Now, one other package of tools that is very useful is related to the quadratic Chabauty method, and that's the computation of p-adic sigma functions and p-adic heights. And this is very useful in the case when you have a bielliptic curve and you can reduce the computation to p-adic heights on elliptic curves. Now there's a construction of the p-adic sigma function due to Mazur-Tate and Bernardi that play a crucial role in computing p-adic heights. And as part of her PhD thesis, Francesca Bianchi gave an implementation of p-adic sigma functions replacing double Coleman integrals, and applied this to the quadratic Chabauty method, and used this to give a quadratic Chabauty proof of Weatherall's theorem on Diophantus's genus 2 bielliptic curve. And Francesca has some very nice Sage math code that's available on GitHub as well. All right, so one of the last things that I like to talk about is quadratic Chabauty and some of the tools that we have for computing with it. So quadratic Chabauty applies in the case where, or at least in what we've worked out, we have a curve over the rationals with genus 2 or more, and the rank of the Jacobian is less than G plus the rank of neuron severity of the Jacobian minus 1. We know that the set XQP2, the quadratic Chabauty set, is finite. And behind the scenes, we can use p-adic heights to write down quadratic Chabauty functions to determine the set of rational points. And we have a package that assumes a number of things. It typically seems to work well for modular curves of genus 2 or more that have these hypotheses satisfied. So we have at least one known rational point. The rank of the Jacobian is equal to G. The rank of neuron severity is greater than 1. And we are working with a kind of good reduction for the curve such that the index of the p-adic closure of the Jacobian inside of J of QP is finite. And if we have those hypotheses satisfied, well, we'd like to then press a button and compute the set of rational points using quadratic Chabauty. Right, so what we do is we like to take our quadratic function coming from the p-adic height and pull this back to the curve in some way. So we take a non-trivial correspondence, this line bundle Z on the Jacobian, that then is trivial on the curve, and we pull back the global p-adic height back to the curve, and we have a local decomposition. So for the local heights HV, we use Nekovar's construction of heights. At L, the local heights are trivial when X has potential good reduction. In general, the local heights away from P take on finitely many values. But for simplicity, we're going to assume that these local heights are trivial for all primes away from our working prime P. And this is the case for a number of interesting modular curves. So there still are things that we can do with this. But in any case, it should be possible, thanks to the work of Alex Betts and Nitin Dogra, to extend this to cases where these local heights are not trivial away from P. Now, the difference, the global height minus the local height at P, this extends to a function on the p-adic points on the curve with only finitely many zeros. And that's kind of the setup of quadratic Chabauty in the instance that we've implemented it. So in joint work with Nitin Dogra, Stefan Mueller, Jan Tuitman, and Jan Bonk, we have some algorithms making this explicit. And we have Magma code for this available on GitHub, along with a collection of examples. And I just like to conclude just mentioning some examples where quadratic Chabauty and this particular implementation has been tried and tested. Though of course we are excited to consider new curves where maybe we don't satisfy all these hypotheses and we have to extend the code in different ways. Or in considering other curves that we haven't yet considered, maybe we'll find some things that we will need to improve in our code. So if you do have a curve which you think might be a good candidate, I would love to hear about it. So the curves that we've considered so far, so this is in various collaborations, but also some work of students and others. So first, the Akin-Lehner quotients of X naught of L. So for L a prime, or here N a prime, just a fixed notation. Here, the genus of the curve is assumed to be between 2 and 6. The first two projects in various collaborations focused on the case of genus 2 and 3. And then last year at the Arizona Winter School, we had a group of students and postdocs looking at the case of genus 4, 5, and 6. And they recently posted a paper on the archive studying rational points on these X naught of N pluses for those genera. And then in the case of composite level N, the case of 169, this is the case of the cursed modular curve, and the case of 125 was handled recently by Michelle LaRue and Stefan Mueller. We also have some examples from Mazur's program B, like I mentioned in the previous lecture, the other level 13 exceptional curve, as well as some other curves with non-trivial local heights. And of course, it would be very interesting to extend all of this to handle curves where we have more interesting non-trivial local heights. I think those are all the tools that I wanted to mention for handling rational points on curves. And thank you very much for your attention. I'll stop here.